Welcome to my first lecture in equilibrium. Today we're going to do an introductory lecture into the concept of dynamic chemical equilibrium. Of course, these are the knowledge outcomes prescribed by Alberta Learning. They form the basis upon which the bulk of the diploma exam questions are set. I'd refer you back to this page from time to time to gain a sense of how well your progress is coming in mastering the material. Up to now, we've always assumed that when reactants are mixed, a chemical reaction takes place automatically. All the reactants will disappear and will be turned into products. That is to say, we assume that reactions are both quantitative and stoichiometric. We saw something different in redox. In redox, we saw that while some chemical reactions are spontaneous, some are not. And when you mix reactants, no reaction takes place at all in certain instances. Equilibrium sort of extends that. In this unit, we'll find out that even if a chemical reaction occurs, it doesn't do so quantitatively. You'll still be left with some reactants even after the reaction has sort of ran its course. Quite often, you'll be left with a lot of reactants, and only a small portion will undergo chemical change into products. Dynamic chemical equilibrium is an interesting condition. Outwardly, it appears like nothing is going on. But in point of fact, what's happening is there are two equal and opposing chemical reactions taking place at the same time. Reactants are being converted into products, but at the same time, products are being converted back into reactants in what's called the reverse reaction. Equally importantly, even if you reach dynamic equilibrium, these two opposing reactions do not stop. They continue to run in opposite directions. It's just that they're running at the exact same rate. And that's central to equilibrium theory. The reactions have reached a point where the rates of both what we call the forward reaction and the reverse reaction are equal. In the end of the day, the chemical system is going to continue to have a mixture of reactants and products. So that the system appears to be idle. There's really nothing measurable in terms of an equilibrium to identify it as an equilibrium. It's just that we need to conceptually understand that there are two opposing chemical reactions occurring simultaneously. A classic example is what's known as the dinitrogen tetraoxide system. It's a colorless molecule that spontaneously reacts. It splits, in fact, to form a brown-colored nitrogen dioxide gas. And in fact, both species are in gas phase. So what happens initially is the brown color becomes more pronounced until the system reaches equilibrium. At that point in time, the color will remain constant. It won't disappear completely. It'll sort of be intermediate in strength between pure nitrogen dioxide and a complete absence of nitrogen dioxide. And what's happening is the system has not stopped producing nitrogen dioxide. It's just that the rate of nitrogen dioxide production is equal to and opposite to the rate of nitrogen dioxide being destroyed in the reverse reaction. And graphically, it looks like this. So from left to right, the dinitrogen tetraoxide, which is colorless, is initially the only species present. So it forms the nitrogen dioxide, which is brown in color. So initially you see an increase in this brown color. Ultimately, once you start producing nitrogen dioxide, the reverse reaction takes place, and it's being converted back into dinitrogen tetraoxide. So that reverse reaction causes the brown color to fade as the nitrogen dioxide disappears. Ultimately, the system reaches equilibrium, where the forward reaction, the production of nitrogen dioxide, and the reverse reaction, the destruction of nitrogen dioxide, are in balance. So there's no further color change. And again, excuse me, that piece is important. We're not talking about equal volumes or equal concentrations of reagents, nor equal masses, nor equal moles. In fact, we'll see that the moles are very, very unequal. We're talking about equal rates of opposing chemical reactions. Essentially, we're looking at how fast opposing reactions take place. For ease of study, we generally examine dynamic equilibriums in closed systems so that neither mass nor energy can be exchanged. And a useful analogy is a soft drink bottle. In this example, not only is a good analogy to a chemical equilibrium system, but it extends the discussion to what's called a stress or a disturbance that we place on an equilibrium system. So when sealed, we got a bottle of pop, and of course it's carbonated. What that means is that under pressure, we've dissolved carbon dioxide into the liquid. And the carbon dioxide in the liquid is in balance with carbon dioxide in the small amount of airspace above the pop. And it's called a phase change equilibrium. And we write it as a reaction like this. So on the left, we have the carbon dioxide dissolved in the soft drink, and it's coming out of solution into the airspace above the soft drink inside the sealed bottle. And at the same time and at the same rate, carbon dioxide in the airspace above the pop is being converted back into dissolved carbon dioxide in the soft drink. So these two processes, in fact phase change processes, are equal and opposite. What happens when we open the bottle? Well, under equilibrium principles, we call that a stress or a disturbance. And I think you can see that the carbon dioxide in the airspace above the beverage will escape to the surroundings outside of the bottle. How will the system react to that? Well, the system wants to reestablish that equilibrium. So it'll shift. We call it a shift. And more carbon dioxide will come out of the aqueous phase, will come out of solution into the airspace above the soft drink, trying to reestablish that phase change equilibrium. But of course, once it enters that airspace, it's going to leave the bottle to the larger surroundings. And the system will try in vain to try and reestablish an equilibrium that it can't reestablish. Ultimately, all the CO2 will leave solution into the airspace above the solution, and then leave that airspace into the greater surroundings outside the bottle, and the drink will go flat, something we're familiar with. This eventuality is aided by a couple of facts. First of all, carbon dioxide is a nonpolar molecule. Water is a highly polar solvent, so carbon dioxide does not dissolve well into water. We only bottle carbonated soft drinks if we put them under pressure. That forces the carbon dioxide to go into solution. Of course, we've all seen you take the lid off and the soft drink fizzes as the carbon dioxide escapes solution. And again, removing the cap is known as a stress or a disturbance. And much of this unit revolves around applying a stress to a system and observing how the system reacts. Equilibrium principles are consistent with the collision theory. If you think about it, just as there are effective collisions of reactants for the forward reaction to occur, there can also be effective collisions of products for the reverse reaction to occur. The final state of an equilibrium can be thought of as a competition between effective collisions in both the forward and the reverse direction, and that's not a bad way to think about it. And again, generally, unless we want to apply a stress to a system, we focus on systems that are closed to avoid the loss of any reactant species or any product species in the system. In this course, we broadly study three types of equilibria. The first is a phase equilibrium, and that's what we just looked at when we looked at the soft drink example. You have carbon dioxide in aqueous phase in equilibrium with carbon dioxide in gas phase. The second is a solubility equilibrium, and we haven't talked about it yet, but imagine dropping a large chunk of table salt, NaCl, into some water. A great deal of it will dissolve, but ultimately if you overload the water with salt, you'll have solid phase salt in contact with a solution of salt water. Now what you're going to have is salt ions, sodium ions or chloride ions coming off the solid phase, coming off the solid chunk of salt and going into solution. But at the same time, you're going to have free ions that are in solution reprecipitate out onto the solid phase salt. So ions will be leaving solid phase into aqueous phase, and at the same time, in the opposite direction, aqueous phase ions will be redepositing onto the solid salt. And then finally, a chemical equilibrium is the third type of equilibrium we'll be looking at, and the dinitrogen tetraoxide system is an example of that. Perhaps an even more famous system is the hydrogen iodide system. We run it at a high temperature, but the molecules are all simple, and the reaction occurs in a gas phase. There's also a very nice color change associated with reaching equilibrium. The iodine is a visible molecule. I believe it's purple in color. It makes for easy observation. Yeah, it's purple in color, and it gradually fades as the forward reaction takes place, and then it remains constant as the reverse reaction gains in the forward reaction to reach equilibrium. And here's the chemical reaction for the equilibrium system. So hydrogen gas is reacting with iodine gas to form hydrogen iodide. Once the hydrogen iodide appears, the reverse reaction commences, and hydrogen iodide is being converted back into hydrogen gas and iodine gas. And we can analyze this system using three different scenarios. The first scenario, we start with a mixture of the reactants in the forward direction, so hydrogen gas and iodine gas. In the second scenario, we start with a mixture of hydrogen gas, iodine gas, and the hydrogen iodide, so all three participants in the equilibrium are present to some degree. And in the third scenario, we start with just the hydrogen iodide alone. So if you run these three experiments, here's an example of experimental results you might find. And you'll see there's three trials here. The first trial starts with just hydrogen and iodine gas. There's no hydrogen iodide. And these three columns correspond to initial concentrations. Equilibrium concentrations are here, and you'll see that in the end of the day, you've got a mixture of all three species present in solution. In equilibrium. Trial 2 is different. Trial 2 has a mixture of hydrogen gas, iodine gas, and hydrogen iodide, all three present, and it reaches an equilibrium position. And then trial 3 starts with only the hydrogen iodide. There's no hydrogen present, there's no iodine present, and it reaches a characteristic equilibrium position. And we'll be looking at these three trials. Actually, we'll be looking at the first trial, graphically and mathematically, because you get some interesting results. So first, graphically, we can examine this using what's called a rate graph. And again, we've talked about equilibrium being a balance in opposing chemical rates. So let's see what that looks like graphically. So you'll notice that the x-axis is time and the y-axis is reaction rate. And the forward reaction, H2 plus I2 going to 2HI, is represented by this curve that starts at some positive value but then slows down. And hopefully this is intuitive. The hydrogen gas and the iodine gas are being destroyed. So it makes sense that as the concentration of those reactants drops, that the rate at which they react should slow as well. The reverse reaction, where hydrogen iodide is reformed into the hydrogen and the iodine gases, starts at 0. And again, hopefully that's intuitive, because in trial 1, and remember we're graphing trial 1 here, we didn't have any hydrogen iodide in the system. So this reverse reaction should start at 0. But then it immediately picks up speed as the hydrogen iodide is formed. Until, and I've lost my mouse, there it is, and picks up speed until ultimately the rate at which the forward reaction takes place is equal and opposite to the rate at which the reverse reaction takes place, and we reach a system in dynamic chemical equilibrium represented by this horizontal line. And just to state that flatly here, the rate of reaction between hydrogen gas and iodine gas starts at some positive value, while the rate of reaction of hydrogen iodide conversion back into these gases starts at 0. Makes sense, of course, since there's no hydrogen iodide in the system initially. At equilibrium then, the two opposing rates are equal, as the rate of the forward reaction equals the rate of the reverse reaction. The second type of graph that describes these equilibria is known as the concentration graph. It examines the concentrations of all species as the system reaches equilibrium. And for that first trial we looked at, it looks like this. And if you remember the values, the concentration of hydrogen and the concentration of iodine are equal, and they both equal 5.00 millimoles per liter. And we had no hydrogen iodide to start with, so it starts at 0 millimoles per liter. As the reaction proceeds, the forward reaction proceeds, the concentration of reactants in the forward direction drops. And they drop at the same rate because the stoichiometry of the reaction is 1 mole of hydrogen gas reacts with 1 mole of iodine gas. So they should dissipate at the same rate. As soon as they start dropping, though, the concentration of the hydrogen iodide increases as it's being formed. Ultimately, the rate at which the reactants of the forward direction disappear slows, and the rate at which the products of the forward reaction slows. The rate at which the products of the forward reaction being produced slows. And we reach a situation where their relative concentrations are no longer changing. So this vertical dashed line is the system reaching dynamic equilibrium. And as we go forward, the relative concentrations of the species remain constant. Now, the important piece here is equilibrium is not about equal concentrations. We see here that the hydrogen iodide is 7 times more concentrated than either the hydrogen or the iodine. Equilibrium is not about equal concentrations, it's about equal and opposing rates of chemical reaction. And again, to say that again, the relative concentrations of hydrogen, iodine, and hydrogen iodide do not change once the system reaches dynamic equilibrium, but they're not equal. We can quantify their relative concentrations using what's called an equilibrium law. To state the equilibrium law, it looks like this. For any balanced chemical system in equilibrium, described as A plus B in equilibrium with C plus D, the equilibrium constant for the system, designated Kc, is defined as follows. Kc mathematically equals the molar concentration of C raised to its coefficient times the molar concentration of D raised to its coefficient divided by the product of the molar concentration of A raised to its coefficient times the molar concentration of B raised to its coefficient. So what we're looking at here is concentrations of products in the forward direction divided by concentration of reactants in the forward direction. And if we apply this equilibrium rate law to the hydrogen iodine system, then the equilibrium constant expression is going to look like this. So Kc is going to equal to the concentration of hydrogen iodide squared, because if you look at the equation, the coefficient of that reagent was 2, divided by the product of the concentration of the hydrogen gas times the concentration of the iodine gas. A couple of general rules surrounding the Kc. Pure liquids have constant concentrations. So we do not include the concentration of liquid phase species in the equilibrium constant expression unless all species are liquid and miscible. And when I say miscible, I mean that they're mutually soluble and highly soluble in one another. It's only then we can talk about variable concentrations. So it's only then that we include liquid phase substances in the Kc expression. Solids, on the other hand, are never included in the Kc expression. Their rates of chemical reactivity is largely dependent on their exposed surface area. So we don't include them in calculating the Kc value. If we go back to our tabulated results then, our 3 trials of the hydrogen iodine system, and we apply the Kc formula to those 3 trials at equilibrium, we get some interesting results. And here they are. So again, the last 3 columns are equilibrium concentrations. In trial 1, if we plug those equilibrium concentrations into our Kc expression, we get a value just a little over 50. In trial 2, if we take those equilibrium concentrations, plug them into the Kc value, we get a value at 49. And in trial 3, we take those equilibrium concentrations, plug them into Kc, and we get a value a little over 51. And keep in mind that these 3 systems started in very different places. Trial 1, we started with only hydrogen and iodine gases. We didn't have any hydrogen iodide. Trial 2, we had a mixture of all three species. And trial 3, we only had hydrogen iodide. We had no hydrogen and no iodine in the system. And yet they all arrive at the exact same Kc value. Well, within a degree of error, they all arrive at the same Kc value. Which raises a very important point about Kc value and the equilibrium position of a chemical system. It's akin to a state function. It's completely independent of the path the system took to arrive at the equilibrium. Keep in mind these three chemical systems started with very different mixtures. In one case, we had nothing but hydrogen and iodine gases. In the third trial, we had nothing but the hydrogen iodide product. And yet they both arrived at the same Kc. They both arrived with the same mixture of concentrations of species. And because of this, Kc values are useful to us in chemistry. The only thing that influences a Kc value for a chemical system is temperature. However, it's completely independent of initial concentration of reagents, as we've seen, the presence of a catalyst, and the time required for the reaction to proceed. Kc values can have units. We're talking about molar concentrations of products over molar concentration of reactants. So you'll expect to see moles per liter show up somewhere. However, by agreement, because the units can get very complicated, we write Kc values without any units. To the extent we've looked at reactions before that were incomplete, we talked about percent yield calculations. And you may remember from grade 11, when we talked about percent ionization of an acid, we used this formula, that the percent reaction, or the percent yield of the ionization of an acid, was the concentration of hydronium ions over the initial concentration of the acid times 100. So if the percent reaction was under 50%, then if we look at the fraction, then the amount of hydronium in the numerator has to be less than the amount of the initial concentration of the acid. Well, if you think about that, that would correspond to a Kc value of less than 1 because the numerator, my mouse has disappeared, because the numerator is smaller than the denominator. Mathematically, if you have a Kc value less than 1, if a fractional value is less than 1, the numerator has to be smaller than the denominator. So percent reaction under 50% corresponds to corresponds to a reaction that where the Kc value is less than 1. On the other hand, if the percent reaction or the percent yield is greater than 50%, then we're going to have a Kc value that's greater than 1 because this numerator is going to be larger than this denominator. And that will hold true as we go forward, as you'll see. So that ends the theoretical part of my lecture. I put a few questions together that you'll find illustrative. Which of the 5 following apply to a chemical system in equilibrium? Okay, and there's 10 choices. Let's see what we have. 1. The rates of the forward and reverse chemical reactions are equal. Yes, in point of fact, that's the definition of a dynamic chemical equilibrium. 2. The concentrations of all reactants and products are equal. Well, no. The concentrations of products and reactants are not equal. They're defined by a mathematical relationship known as the equilibrium constant expression, or Kc. 3. Once equilibrium is reached, there's no change in concentrations of reactants or products with time. Yes, that's true. 4. Once equilibrium is reached, the concentration of reactants and products fluctuate with time. No, not true. 3 is true, 4 is false. 5. Once equilibrium is reached, a smooth transition from one color to another is visible. Not true. 6. Once equilibrium is reached, no empirical evidence of a system in equilibrium can be seen. And that is true. Equilibrium is often referred to as the chemistry of nothing because nothing appears to be happening. 6. Once equilibrium is reached, no empirical evidence of a chemical reaction is happening. Well, I just said that. Yes, that's true. Number 7. The system reaches equilibrium position if all species start with certain fixed concentrations. No, not true. We just looked at the hydrogen iodide system, and we started with 3 very different initial concoctions, initial concentration levels, and all three reach the same equilibrium. So therefore 8. The system reaches an equilibrium regardless of the initial concentrations of all species. Yes, true. 9. A system in dynamic equilibrium is like a tug-of-war with both teams pulling with equal force on both ends of the rope. Well, let's look at 10. A system in equilibrium is like a border crossing where traffic constantly moves back and forth across the border, but the populations of the two adjoining countries are stable. Yeah, I prefer 10 to 9. 10 includes that sense that you have two equal and opposing processes taking place that don't impact on the neighbor, the relative populations of the countries. So I prefer 10. Therefore, the answer is 1, 3, 6, 8, 10. Hopefully you did well. 2. Which 4 of the following apply to the equilibrium law for a system in chemical equilibrium? And another 8 choices. 1. The Kc reflects the ratio of concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. Yeah, that's true. 2. Liquids are always excluded from the Kc unless all species present are in liquid phase and are immiscible. Yes, that's also true. 3. Liquids are also excluded from the Kc. No. 4. Solids are always excluded from the Kc since their concentrations are constant and the rate at which they react is dependent upon the exposed surface area of the solid. Yes, that's true. 1, 2, and 4 so far. 5. If the Kc equals 0.20, then the system at equilibrium will have higher concentrations of products and reactants. Well, we're talking about a Kc value equal to products over reactants. If products have a higher concentration than reactants, you can have a Kc value greater than 1. So 5 is false. 6. If the Kc is 1.5, then the system will have a percent yield that is lower than 50%. Well, no, if products over reactants equals 1.5, you're going to have more products than reactants, and the percent yield is going to be greater than 50%. So 6 is false. 7. The Kc value is a theoretical concept that has no units. Nope. 8. The Kc value has various units depending on the chemical equilibrium under consideration, but by agreement we drop the units. That is true. Final answer, 1, 2, 4, and 8. Circle the correct Kc. We're looking at concentration of NO to the 4th power divided by the product of the concentration of N2O to the 2nd power times O2, and that appears to be D. Circle the correct Kc for the following system. Well, we have to be mindful that the reactant here is in solid phase, and so is the first product. We ignore both of those, and the Kc is going to be the concentration of CO2 times the concentration of H2O, and the answer is A. A mixture of carbon monoxide and hydrogen gas is used as a fuel source. At high temperatures, the reaction of coke and steam forms an equilibrium in which the products, the carbon monoxide and the hydrogen, are favored. Choose the appropriate chemical reaction. We're looking at a reaction between coke and steam, which is H2O in gas phase. So A is out and B is out. C and D are both coke with steam, and it says the products are favored. So the reaction proceeds greater than 50%, and that corresponds to D. This fish mouth here pointing in this direction says that the reaction proceeds greater than 50%. Answer is D. One last question. Match each Kc inequality with one of the choices. If Kc is greater than 1, then the concentration of products has to be greater than the concentration of reactants, and the answer is A. If Kc is less than 1, then the reactant concentrations have to be greater than product concentrations. The answer is D. If Kc is very much greater than 1, then the products have to be greatly favored. You're talking about a fraction where the numerator is much larger than the denominator. And then finally, where Kc is very much less than 1, we're talking about reactants having a very much higher concentration than products, and the answer is B. That concludes a long and somewhat rushed introduction to equilibrium. Hopefully you found it of some value. I'll refer you to your teacher's homework, and we'll see you next time when we do some quantitative work on Kc values. Thank you.